So, dear madam, thank you for representing me. I am working in Poland, in Lublin, University of Maria Curie Skłodowska, and I chair of cybersecurity department in Ukraine, Institute of Telecommunication and Global Information Space. So title was given, but I have to say, of course, that it's my pleasure to take a floor here at Isaac Newton Institute and present some topic. Actually, this topic is about famous sequences of graphs of large girths and small word graphs. The difference here with known results is that the density is maybe infinite, and number of neighbors in such graphs can be infinity. So we will go to some algebraic manifolds. So in probability theory, branching process is a special stochastic process corresponding to a random walk on a regular forest F, i.e. simple graph without cycles with vertices of the same degree, finite or infinite, of cardinality bigger than 2. The genealogy of a single vertex is a tree. So I'm talking about forests because the graph not necessarily has to be connected. The forest itself, F, is a deterministic part of branching process. We investigate a possibility to define that forest by system of equations over the field or special commutative ring K, i.e. as projective limit of homogeneous algebraic graphs GI, I equal 1, 2, and etc. over K. So a homogeneous algebraic graph G is the graph in which sets of vertices and edges are algebraic varieties over K. So I mean here we use Zariski topology, such that the neighborhood of each vertex are isomorphic to the same algebraic variety, which is given n(gk). Recall that the girth of G of the graph is the length of its minimal cycle. In the case GI, at least some constant ni, where ni are dimensions of the vertex sets, because they are manifolds that have dimensions of the graph, we will use term algebraic forest approximation of large girths. So we have here well-defined projective limit. So it means that from larger graph to smaller graph has to be established some graph homomorphism, and each member GI is algebraic graphs, maybe of the same valency as the variety and GI, and we in this case will talk that we have algebraic forest approximation of large girths. So this graph GI, which has finite dimension, approximate an infinite graph which is defined as projective limits of GI. Of course, the first examples were investigated over definite fields, and the first example of such families GI, and so-called family DNQ, where Q is prime power n equal 2, 3, and etc., were presented in publication of Felix Lazebnik and myself in Bulletin of American Mathematical Society. Actually, these graphs D and Q are disconnected. So if n going tends to infinity, we will get forest, not a tree, but the construction of trees of this algebraic forest were investigated by Philip Lazebnik, Ustimenko, and Walder. This is Bulletin of American Mathematical Society, 1995, number 1, January number, January volume of this graph. So that maybe I just say directly that we can do some algebraization to change this finite field FQ for arbitrary integrity ring K. So K can be now real numbers or complex numbers or interval 0, 1, so fractions with additions and multiplication. So in the conference devoted to Georgy Voronoi in 98, I proved that the girth is in fact bigger or equal n plus 5. So for this d and k, so girth is growing with n in fact, and it's infinity. So we have forest if n tends to infinity. So here, important that I can say, for instance, I can take, for instance, dnfq, where fq is finite field. But now after, so this is a family of algebraic graphs. But after I can expand it to the dn, this fq x1, x2, xm, a polynomial ring from invariable x1, xm. So we will get the same law for increasing girth n plus 5, and it can be used in computer science in theory of symbolic computations. In fact, with Tony Shaska from Michigan University, we proved that the girth of this graph over the field F of characteristic 0, in fact, equals n plus 5, not just lower bound, but equality. So we say that infinite algebraic graph GK, which is limit of GI algebraic graphs over K, has small word approximation by GI if diameter dGi is bounded from above by constant times ni for some positive constant. Note that this definition coincides with well-known definition from Random Graphs book by Balabash in the case when we have finite fields. So we have family of graphs of the same degree, K, and diameter is bounded from above by some function C log Vi, where Vi is order of graph Gi. That's in the finite case. But here specific that we are working not necessarily with finite fields. So the first small word approximation was obtained by Vyacheslav Kutorny and myself. That is publication of Acta Applicandae Mathematicae 2007. And projective limit of these graphs is Wenger graph. So I have to say that this is not Arsène Wenger, the coach of Arsenal. This is American mathematician Robert Wenger. And this is not a forest approximation because Wenger graphs has cycles of length 8. They doesn't have small cycles of length 3, 4, 5, but unfortunately they have C8. So the question about small world approximation of the forest or a tree was still open. So maybe I have to say that in finite case, very well-known family XPQ, so-called Cayley-Ramanujan graphs, which were defined by Gregory Margulis. While he was working in Institute of Information Transmission in Moscow, now this Kharkiv Institute. And the girth and diameter and eigenvalues, in fact, the spectrum of these graphs were investigated by Alex Lubotsky from Israel, Peter Sarnak from United States, and Phillips. So actually, so we have here we have Cayley. We have a group PSL2P, and we have a Cayley graph with special generators, alpha 1, alpha 2, alpha q, where q is another prime number. Now, when we p tends to infinity, we are getting an infinite family of graphs, and the girth is growing quite fast, and diameter is bounded again by logarithmic function. So we have a very nice object which is at the same time family of graphs of large girth and family of small world graphs. And in fact, this is family of expanders. The gap here, q valency minus 2 square root of q minus 1, so they so-called Ramanujan graphs, actually. So, but again, here the problem, these graphs doesn't form forest approximation according to the above definition because of absence of homomorphism between xp1q and xp2q, where p1 and p2 are different primes, because you see the groups PSL to p1 and PSL to p2 are simple groups, so it's impossible to find normal divisor. So that the situation in case of finite fields. But very recently, this is stated because of application to cryptography in International Association of Cryptology Research e-print this year in last month. The following theorem was stated that for each field k bigger than 2 of odd characteristic, there is a small world tree approximation of large girth defined over k. So we have the family of large girth, which is a forest approximation, and because graphs all connected, we have to say about tree approximation. So, and the diameter of these graphs are nice, so they form a family of small world graphs in the sense of Bella and Bolabash. So, in fact, the statement was proven via explicit construction. This homogeneous algebraic graph Rnk, where k is arbitrarily commutative case. And this is introduced in 2007 even in Journal of Mathematical Science. So the result was presented at some conference in St. Petersburg. But only now the new theorem was obtained. The difficulties, the technical difficulties to prove that this is the family of large girths was connected that this graph is not edge transitive. So there is not absent nice group to work with this group. But finally, this theorem was stated. So now I defined this graph. So this, in fact, simple thing, we will consider a tree, which is Q-regular, given by equations. So what we have to do, that maybe for simplicity, K, let's be finite field FQ. So we are taking two Cartesian power of this FQ, two vector space of dimension n. P stands for points and L stands for lines. So we will write P1, P2, Pn, the brackets. This is in the case when we have element of P, because we have two copies of Cartesian power K. And L parenthesis when we have line L1, L2, Ln. So we have, we will define bipartite graph because everybody knows that infinite tree is in fact bipartite graphs. So so we have points and lines and equations between them of the following kind. P2 minus L2 is L1 P1, P2 minus P3 minus L3 P1 L2, P4 minus L4 is L1 P3, P5 minus L3 is P1 L4. So what is the recurrency here? So left-hand side are differences of coordinates, Pi in Li, but in right-hand side we have monomials, simple monomials, where first coordinates P1 and L1 always presented. So L1, P1, L1, P1, and so on. And if we use L1, we need to use Pi. And to care about it, here you see 1 plus 1 is 2 from the left, 1 plus 2 is 3 from the left, 1 plus 3 is 4 from the left. And so we can go, and of course, the last equation depends from the case when whether or not n is odd or even. In both cases, it's explicitly written. First theorem, which was what was proven in 2007, that if K is FQ, Q bigger than 2, then projective limit of these graphs, because these graphs depends from n, but we can take n and move it to infinity. So it means that we simply have take all this equation, P2 minus L2, Pn minus Ln, and etc. till infinity. So this is equations of the tree. So we have algebraization of this this graph. The first was theorem was that this is projective limit. Of course, it's well defined. It's clear from the equation. Is a Q-regular tree here. This tree for Q equal 3 is depicted. So we have branching process, some root, and 3 neighbors, and this next vectors has also 3 neighbors. One is above and 2 are below. And when we continue this branching process, we will get a tree. So these graphs are appears very nice for as tools for construction low-density parity check codes. In fact, low-density parity checks codes were constructed from the graph, Kelly-Ramanujan graph by Margulis, but the properties of new graphs, new codes obtained from ANFQ are much better. So actually, we have various application of these results. Here, recently, we discovered a bound that girth of R and Q bigger or equal n+2 divided by 2 flow functions. So this is lower bound, which give us the fact that for such K, we have K is integrity ring. We have a family of algebraic graphs of large girths. And application, of course, people here on the probability side, and instead of finite field FQ, it's interesting to take commutative ring R01. All real numbers in this interval, 0 is included, but 1 not. This is famous ring. And or we can take all rational numbers from this interval. So what about the applications to of this graph? One application is that in the paper of Bardi and Paul recently was introduced the concept of time in Markov process. And the concept is this is a graph. The time can measure by graph, and it has to be special time-like graph. And all graphs which are introduced here, this A and K, where n tends to infinity, they are time-like graphs. So they are appropriate tools to measure the to measure the time in Markovian process. Others think that there is paper about fractal graphs. There is so-called fractality problem. Fractality properties of graphs, it comes from construction by Sierpinski budgets, and actually nice problem is compute fractality and investigate fractality property of these graphs. But actually they are expanding graphs in sense of Alex Lubotsky. About expanding graphs, we can talk only in the case of finite field FQ. So spectral gap here, 2 square root of Q. It could be proved that they are almost Ramanujan graphs. And of course, the algebraization of branching process, 3 is equation, can be used in many cryptographical applications. So here the many references can be done. In fact, we can consider semigroup of all walks on AFQ or ANFQ of even lengths. And here that it allows to define transformation groups on the vector spaces over FQ or over other commutative rings. These groups are interesting that they have stable degree. They are cubical transformation forming this group, the degree of less or equal than 3. So this is unusual that composition of 2 transformation of degree 3 is not 9, but again 3. So this fact is used in post-quantum protocol of non-commutative cryptography. So these results have to be presented in my plenary talk and mathematical aspects of post-quantum cryptography in Kaliningrad, by obvious reason that terroristic attack of Russia against Ukraine. So I just have to say that in time of the Kaliningrad is historical Königsberg. So in time of Euler, who was Gastarbeiter from Switzerland to Russia, and was working on the bridges in Königsberg, so it was part of Europe and safe place as well in time of Immanuel Kant, but not now, especially to arrange the conference at the university, which was opened formally by Schröder and Putin. So this is crazy idea. So I ask all invited speakers don't participate in this event. Thank you very much for your attention. I rather leave some time for possible questions.
Yes, thank you very much for your talk. Let's thank the speaker. First, let me turn to the audience here in the room. Are there questions? So let's try to find out. Peter is not here. Please, if you have a question, unmute. Concerning the, I'm addressing the virtual participants. Please unmute and ask your question. It does not seem to be a question right now. I'm personally not in graph theory, but the question that occurred to me, I mean, your construction, above your construction, I mean, there are weighted graphs. So of course, you could also have a weight or a random variable on the edges. Does this seem adequate for applications?
Okay.
I mean, you had the application of coding theory.
So coding theory, actually, Markovian process is time measurement. Actually, it can be in Bössendes processes, because in infinite graph we can consider the particles. And here, interesting case where the degree of graph is not bounded, so known results can be, in some case, modified. So this maybe for Böss and Des processes, it's interesting objects. According to your nice idea to use graphs with weight, here it will be some problem, because I consider simple graphs, so they have no weights. And in this case, the girth is defined as length of minimal cycles. But if we have weights, I believe that we still can consider small word graphs, the same definition. So it's growing because metrics can be constructed on the graph with weights, so diameter can be behaved as a logarithmic function. But about the girth, it's in fact not straightforward. Thank you. It's a nice question. Maybe tree with weight is also nice object, but I have to think about. Thank you.
Thank you very much for your answer. I look again, please, if there is a question from the audience, virtual audience. Ray, yes. Jose? No? Okay. Then let's thank the speaker again.
Thank you. Thank you, all of you.
But it's also a beautiful platform, very beautiful time, to establish scientific methods, but also to create new scientific methods. I cannot underestimate thank you very much for this. I think Vasyl also
very well said about the Newton Institute, actually, which I also wanted to say, to thank you, Newton, for the possibility of meeting here. So Astrid said everything very well about it. So from my point of view, I just want to thank all the participants who really came in this difficult time. I want just to stress that we really tried to do our best under all these difficult conditions. And so hope it actually was not as bad as it could be. So thanks for coming. I also would like to thank all other organizers. We have somehow a big group of people who took part in the organization of the thing. Here's only Michael present and me, and unfortunately other organizers were not able to be present here. So, but they all contributed very hard to what we managed to achieve here. So thank you everybody for coming, and I also wish you, if you still stay here for the remaining part of the program, so wish you success in the research. And just one technical remark is that actually, of course, Newton Institute is interested in somehow traces sort of this program. So whenever you have some papers, researches, ideas, so there is this, I just remind you that there is this preprint series. Please put your papers on this preprint series. Also, if you have some publication, please make sure that acknowledgements say, well, we are inspired, or we think to for when the ideas of the paper somehow will be reflected in your further publication. That's all I have to say. Thank you.
So we discussed and about and with Vasyl, you did not take it up, but there is suggested a discussion session. But so we think that this is the end of the conference. Okay. Thank you.
Thank you.